everyone, this is Mr. Tukin, and we're going to spend a little time today analyzing quadratic functions. Now, the focus of this will just be on standard form of a quadratic function. And when we say a standard form, what we're looking at is you're usually going to see y equals. Now, it's okay to have function notation. So you could have like f of x, or just something that names the function and then the input variable, or you could have p of t. All right, we could see something like that. And that's just another function notation where the name of the function is p and the input variable is t. But anyway, no matter what, if you have it written with y equals, the format of your quadratic function is going to be something like ax squared plus bx plus c. Now, a, b, and c are just numbers, okay? It's the x's that you're going to notice. So f of x, you may see, for example, you could see 3x squared um, minus 5x, we'll say minus 2. So if you have this example, the value of a is equal to 3, the value of b equals negative 5, and the value of c equals negative 2. Very common mistake is students will like grab x and like say b is negative 5x. And it's not, it's just negative 5. Now, first off, let me backtrack. Let me apologize for my penmanship. It's obviously going to be very bad, just kind of drawing with a mouse. But anyway, another example, and I always like just throwing this one out there, is we could see something like negative 10. Now my input variable is t, so you're going to see negative 10t squared, and let's say plus 1. Well, in this case, just to show it, the value of a in this case is equal to negative 10, and b, well, that can be a little confusing. What happened to b? Well, in this case, there is none. So that's the equivalent of saying 0t. If you have anything times 0, it's just going to equal 0, so it kind of disappears from the function. So if you see that, it's still a quadratic function. It's still technically in standard form. It's just that your value of the middle term, b, is 0. And in this case, c would equal positive 1. So this is a quadratic function in standard form. Now, as a reminder, with a quadratic function, I've pulled up here an online graphing calculator, desmos.com. It's an excellent one to use. And you could type in function notation, but if you remember, if we just throw in, let's say 3x squared, it's going to start graphing. If it was just f of x equals 3x squared. And as a reminder, if we just see this, it's technically in standard form where a is 3, but b is equal to 0, and c would be equal to 0. And we can even see that if I turn around and do a plus 0, it gives me the exact same function as if I don't have the plus 0 there. So this would be, it's going to start to graph for us. So let's go ahead and do minus 5x. And you can see the shift it has. And then plus, oops, I don't want that. Let's do minus 1. So we can see the quadratic function. The quadratic function is going to graph a parabola. That's this little U shape that's very symmetrical about the vertex. The vertex is right here. The vertex is located at either the very bottom of the function or the very top of the function. And you might be saying, well, how's it the top of the function? If it's a standard form function, if the a value is negative, it flips the parabola around. So instead of it opening upward, notice how it flips it and it opens downward. Okay? So you've got some other things that might happen here with the vertex. And it obviously can change, the location of the vertex, but the opening of the parabola is the biggest thing we take away with it. So I wanted to point that out. I also want to point out, sometimes you'll be asked about the x-intercepts. Not really going to worry about them today, but you can see the x-intercepts. You can see a y-intercept right there. Another thing that's not on this graph is called the axis of symmetry. Now, if I could draw an imaginary line straight through the center of the parabola, that equation of the line is our axis of symmetry. Imagine a mirror. If there was a mirror put down here, and you would see the left side, you would see the right side. It's perfect. It's perfectly the same distance. So if I put a mirror right down the middle, and I'm thinking about like right here, the distance to here would be the same as the distance to this side of the parabola. That line, that equation of the line, is the axis of symmetry. And for the purposes of our quadratic functions, they're always going to be an x equals equation. So let's go back to our little board here. Let's create a quadratic function. So I've put this axis of symmetry on the board, or this, excuse me, this quadratic function on the board. And one of the very popular questions is to match up the axis of symmetry with the quadratic function. And there is a fairly simple formula to use. Now, the axis of symmetry equation will always be x equals. It's x equals some number because it's a vertical line. You can review equations of vertical lines in other parts of your math course, but just for the sake of this, axis of symmetry is a vertical line. The equation for that is negative b over or divided by 2a. Well, do you remember when we said the format is a, b, c? Ax squared plus bx plus c is our standard form quadratic function. So all you have to do is be able to identify a, b, and c. So in this case, b is positive 12. I always say it's a good idea to just throw the number inside parentheses, get in that habit. And the reason is if this number was negative, if let's say it was 3x squared minus 12x, well, that's going to create a double negative, which will make it positive. But if it's positive, you realize that, oh, well, it's going to actually end up as a negative number in the numerator of this fraction, of this ratio. So we've got the value for b, and now we've got to do 2 times a, and a in this case is 3, positive 3. So if the function is just asking you to find the axis of symmetry, you literally can just go into the function, and you're going to end up with negative 12 over 6. If you can simplify this fraction, you need to. Well, negative 12 divided by 6 is negative 2. So the axis of symmetry on this is x equals negative 2. Now I want to show something pretty cool. Remember what we talked about. So I just remember 3x squared plus 12x minus 5. Let's go to Desmos. Let's graph that and look for a minute at it. So I've got that other function up here, but our function that we created was 3x squared plus 12x, and it was minus 5. Now I'm going to need to use a little Desmos. You can kind of scroll out by kind of zooming out with these buttons, or there's a little shortcut. But remember the answer? The answer was x equals negative 2. Notice if we come up here, you can see this point. It's at, from the origin, which is up here, 0, 0. It is 2 spots over. It's at that x equals negative 2, the vertical line, x equals negative 2, through the center of the quadratic function. So that formula, which again was x equals negative b over 2a, does work for finding the axis of symmetry. But that's also going to tie in to the next thing we want to look at. The next thing we want to look at is the connection between the axis of symmetry and our vertex. Remember, our vertex is not just a single thing, it's an actual point. It's an actual point. It's the point at the very bottom of your parabola if it opens upward, and this one does. Or if we wanted to flip it, it's going to be, and this is going to disappear on us a little bit, but, or remember if that negative up here is negative 3, you know, the vertex is the very top point. But let's go back to our original one. So remember that x equals negative 2? Look at the connection between the vertex and the axis of symmetry. Remember, oh, let's do this. X equals negative 2. I've created that vertical line through here. So we can see that it goes right through, but also notice that the x coordinate of your vertex will always match the axis of symmetry. That's a huge connection that you can make because it's got to happen. The vertex is in the center, and the axis of symmetry is always in the center of your parabola. So another thing we can add on to our notes is that the axis of symmetry is always equal to the x coordinate of your vertex. And we could throw on here a little, hey, just as an example of the one we had above, right? X equals negative 2, and the x coordinate of our vertex was negative 2, and I believe it was negative 17 in the example we saw. Now, here's another thing. If we know the coordinate is negative 2, The way they got the negative 17 was to take this value and plug it in for x in our quadratic function. And by running the numbers, we will end up with negative 17. Let's just see that in action real quick. So what I did right here was, you can see I have my input value of negative 2, and I've plugged it in for x in the original function. Now we need to use order of operation, which says we have to do our exponents first. So after doing that, a negative times a negative would give us a positive. And now we've just got multiplication. So we can multiply this, which is going to equal negative 12. We can multiply that, which is going to equal negative 24. And actually, I made a mistake. I didn't mean to put a negative here. So those of you that probably caught that were like, what the heck? So this will actually equal positive 12, and this will equal negative 24. And finally, once we have all that, when we have addition and subtraction, we work it from left to right. So 12 minus 24 is actually negative 12. And negative 12 minus 5 does equal negative 17. So that just means that we proved where the vertex would be located. When x is negative 2, the entire function ends up equaling negative 17. So a lot of times you're asked just to find the x-coordinate of your vertex. Well, or the x-coordinate of the vertex. Remember, that's just the axis of symmetry. You just need to get the axis of symmetry, which is right here. And you could compare different functions with this. You could compare two different functions, and you just basically apply this formula. Very last thing I want to cover is domain and range. Now, if it matches this format, here's a little shortcut. The domain will always be all real numbers. As a reminder, domain is what can x be? Is there any limit to what x can be? And you can actually see it on the graph sometimes. So I always like to throw up the graph. If you think about it, yes, this parabola is going up from this point, but it is also going to the right, and it is also going to the left. Left and right movements are our x-axis. And even if I scroll out forever and ever and ever and ever and ever and ever and ever, yes, it is going up forever and ever, but if we look, it's still going to the right, and it's going to continue going to the right forever and ever and ever. That's why it's all real numbers. According to the graph, there's no limit to what the x value can be. Range is the same idea. Range ends up being, what can y be? Y is our vertical axis. Y does have a limit. And the graph is what helps us to see that limit. If we look, yes, it's going up, up, and up. This red arch, this parabola, is going up, up, and up forever. But is it ever going to go below the vertex? And according to the graph, no, you can see it. So the limit here is y must be all these other y values. If we go on the slider here, notice how the y values are always increasing. They're increasing. They're never below negative 17. So a statement on the range can be y is greater than or equal to negative 17. Because yes, it starts there, right? But then the rest of them go up from there. And conversely, if your parabola opens down, remember we said if this a value right here, if this a value is negative, your parabola opens down. It's still going to have this vertex issue. It's still going to need the y coordinate from your vertex. But now instead of greater than or equal to, because all the values are below it, they're all less than this value, you would use a less than or equal to symbol. So that's essentially domain and range. So for the purpose of analyzing quadratic functions in standard form, we're going to use the axis of symmetry formula to get the axis of symmetry, the equation of the axis of symmetry. But don't forget, this axis of symmetry always runs right into your vertex. So it's going to give you the x-coordinate of your vertex, and if you're actually asked to get the actual vertex, that's the x and y value, it's the location on the graph, it's the location on the graph, so it needs an x and y value. To get that, you would go back to the quadratic function, plug it in, and find out that y value. Hopefully that helps. As always, reach out to your teacher for more support.